To write reliable JavaScript, we can't allow our data to float freely in memory. We must store it in specific, highly controlled containers. This animated diagram shows our two modern options: a standard cardboard box labeled let and a solid steel safe labeled const. The let box is designed for change. You can open it, take out the winter sweaters, and put in summer t-shirts. The contents are mutable. But the const safe is entirely different. Once you drop your data inside, it locks shut permanently. That data becomes immutable and can never be swapped out or overwritten. Let's look at how we build these containers in code. This diagram shows the exact syntax. We start with the initialization keyword let, followed by our unique identifier h. Then we use the assignment operator, the equal sign. Notice how the equal sign acts like a directional funnel, taking the numerical data on the right and pouring it directly into the container on the left. Locking permanent data into a const safe, like a user's unique ID, ensures the engine will reject any later attempt to reassign that variable name. You are setting a guardrail that keeps that identifier bound to its value, preventing other parts of your code from accidentally changing it. Now, watch what happens when we try to update that mutable let container incorrectly. This diagram shows an attempt to change the age to 26 by writing let age equals 26, right beneath the original declaration. The application will crash immediately with a syntax error telling us the identifier has already been declared. You cannot create two identical containers in the same space. To fix this, we simply drop the initialization keyword. Once the let dissolves away, we are successfully targeting the existing container and updating the data inside. Memory containers are only half the architecture. The JavaScript engine also strictly categorizes the actual information you drop inside those boxes. These core categories are called primitive data types. This animated sorting mechanism maps out the three most common primitives. We have a number bucket for all mathematical counts, integers and decimals. We have a string bucket for text data, which the engine recognizes because it is wrapped in quotes. And finally, a Boolean bucket, which handles simple binary logic like a true or false checkbox. Understanding exactly which bucket your data belongs in is crucial. If the JavaScript engine misidentifies a string as a number, or vice versa, it will misinterpret your mathematical intent, leading to silent bugs that can corrupt your entire application. Let's see that exact corruption happen in a standard e-commerce checkout. This diagram shows a string variable price1 set to 100 in quotes, representing text input from a user. Below it, we have a pure number variable, price2, set to 50, representing a back-end discount. We feed both into an addition equation to calculate the total. Take a close look at this equation. Pause the video right now and predict the exact output that will print to the console when this executes. The output is not 150. It resolves to 1050. This is the mechanical flaw known as implicit type coercion. The engine encountered a data type mismatch and tried to fix it automatically behind your back. The addition operator in JavaScript wears two distinct hats. It performs standard mathematical addition, but it also handles string concatenation. If the plus operator detects that even a single piece of data is a string, it abandons mathematics entirely. It converts the remaining numbers to text and glues them together end to end. To solve this, we must force the string data into a true number before the addition operator ever touches it. This diagram shows the explicit casting solution. By wrapping price1 inside the number function, we safely strip away the text formatting. The addition operator now sees two pure integers and correctly outputs 150. But you have to be exact. JavaScript is strictly case-sensitive. You must use a capital N for the number function. If you try to cast using a lowercase n, the engine will fail to recognize the command and throw a reference error, halting your script. Explicitly converting your data types ensures the engine performs the specific operation you intend. Manually overriding type coercion prevents user-submitted strings from silently breaking the logic of your arithmetic. We can synthesize everything we've covered into one clean, bug-free script. This diagram shows our capstone code. We establish our immutable username Alex as a const. We declare our mutable cart total as a let, initialized with the string 20. Then we apply explicit number casting before adding 10 to our cart, arriving at an accurate total of 30. Let's trace how the JavaScript engine reads this. It locks the username in the first line. It prepares the mutable box in the second. Then it evaluates the inner parentheses, converting the text 20 to an integer before executing the addition safely on the final line. To maintain this precision in your own projects, let's establish a few operational baselines. This split-screen cheat sheet outlines our first rule: default to const. Setting containers as constants prevents accidental reassignment. Only switch to let when the value must change. Avoid the outdated var syntax entirely. Next, when you do update a let variable, never redeclare the initialization keyword, or you will crash the script. And finally, treat all user input as string data. Never trust the addition operator to perform math with an unverified input until you explicitly cast it as a number. When you control your memory architecture and account for type constraints, you eliminate the logic errors caused by hidden conversion. These fundamentals allow you to build scripts that produce the same result every time they execute.